Good morning, everyone, and welcome to MAE 209 Probability and Statistics. My name is Richard Kohar, and this is Lecture 22. And let me just... Lecture 22. And in today, we're going to talk about the covariance, the correlation, and conditional distributions, and these are of the joint random variables. And I think I saw some questions in the chat already. Are the midterm marks that are on Moodle right now accurate? I'm not sure what that means. The marks, I think I put them as percentages. If you have any concerns about what you think that the marks should be, feel free to send me an email. I've also posted the average for the course for the people. I posted the average for the class, so that's on Moodle as well. Yep. Yes. So as a warm-up exercise, did everyone try it from last time, which was, what is the expected value of x, y? And if you did it, you should have got this. So again, very similar to how we were doing it last time, that if we have some function that we're using, and we're going to integrate, then it's the function times the probability, and then we have our differentials. So again, we can replace the h. Again, it's going to be just itself then x, y. So that's just the identity. So you would just use x times y times the probability, and then you would integrate for x and then integrate for y. So for the past couple of lectures, we've been discussing joint random variables. And joint random variables just consist of two or more random variables. So you can think of this as just a multivariate case. So we're going from the univariate way to the multivariate. And again, that's like in first year we had calculus, we did single variable. And then when we do second year, it's usually a multivariable calculus then. So just as a little bit of a summary then, when we do have the univariate and the multivariate, we have the probability mass function, or the PMF, and that's for the discrete case. And if we go into the multivariate, then we have the joint probability mass function. If it's continuous for the univariate, it's the PDF, or the probability density function. And in the multivariate, it's the joint probability density function. The thing that we don't have in the univariate, which we do in the multivariate, are the marginal PDFs. Those are where we're kind of calculating, along the margins of a table, or we're integrating along a certain direction to eliminate that variable. We have the CDF, which is the cumulative distribution function, and you can also have a joint version of that for the multivariate. We have expected value in the univariate, then we have expected values. We have variance. We also have covariance, correlation, and these are probably two new terms that we'll see in the multivariate, but we also still have a variance as well that we can define. So the covariance is used to determine the relationship between how two variables move or vary with each other. So we can recall that if we think of the covariance, this is what we had before. It's the expected value of x minus the expected value of x. And we multiply this by y minus the expected value of y. So you can think of this as the distance between x and the mean, and the distance between y and the mean, and we're looking at the expected value of that. So in the discrete case, just move this over here then. In the discrete case, what we get is, again, this is what our function is. So we can write down our function in here. We have x minus the mean of x, y minus the mean of y, and then we multiply it by the probability. And that's for the discrete case. If we have the continuous case, then all we have to do is switch from the summations to the integrals. Now, if you want to calculate the variance of x is equal to the covariance of x and x. So all you have to do then is just, again, not y, it's two x's. So you get x minus the mean of x and x minus the mean of x. So this becomes x minus mu of x squared. And that is what our definition of variance is. The same thing holds then for y as well. So we could do the variance of y is equal to the covariance of y comma y. So just going back to what our covariance is. If the two variables tend to move together, they are seen as having a positive covariance. And if the two variables tend to move inversely to each other, the covariance is negative. So what does that mean graphically? Here's the three cases that we can think of. We can have them where they're kind of trending upward, like this direction. We can have them moving downward diagonally, so upward diagonally, downward diagonally. Or we can have kind of this scatter shot here. So in this, again, if the two variables tend to move together, they are seen as having positive covariance. So because they're moving together, they are seen as positive covariance. And again, if they're moving inversely to each other, then they're considered negative. So you can see kind of the general direction that we have here. This is positive, it's going upward, and negative, it's going down. Now, when you have something like this kind of circular pattern, we say that there's zero covariance. So I'll just number this. This is number 2. Now, what we can do is we have a property that, this was a formula that we had done before. We had the covariance of x and y, and you can also write this as the expected value of xy minus the expected value of x and multiplied by the expected value of y. So here's a small proof for doing this. So and again, that's what we need to try to prove. Okay, so what I will do is I will start to distribute this. So again, I can distribute that to here. So what I get is x, y, and then I'll have minus x mu y. Then the next one that I need to do, grab another pen, let's use red. I'll have minus y mu x, and then positive mu x mu y. So I can apply these the properties of the expected value. So I can apply the expected value to each of these terms. So let's say expected value of x, y, and I'll do minus the expected value of x mu y minus the expected value of y mu x plus the expected value of mu x mu y. Okay, so I can leave this alone because it's the expected value of xy. The thing that we need to recall then is that the expected value of a constant times a random variable is equal to the constant times the expected value of the random variable. So I can bring basically the a out. Now what's interesting about this is that mu y is not a random variable, but it's actually a constant. So I don't have to apply, well, I can just bring out that in front. And I don't know why I put an equal. So what I have then is the expected value of x times the expected value of y minus expected value of y u of x. And then right here is a constant, so I can just leave those alone. U of x, u of y. The next thing I can do is I can rewrite expected value of x and the expected value of y. Here I can actually write that as mu of x. Here I can put this as mu of y. So same thing here. I'm just going to exchange the mu x and mu y plus mu x mu y. So I can cancel out this one and this one, and so I'm left with what we were required to find, the expected value of x, y minus mu of x, mu of y. And so that's what we've shown. That's what we needed to do, and we're done. So is there any questions in the chat about what I did there? Okay, I think there's no questions, so I'll move on to the next. Here we go, and here's number 4. So another measure that we have is called the correlation. And the correlation is a measure of how much of a linear relationship exists between two random variables, x and y. So the correlation coefficient of x and y is given by this formula right here. So it's the correlation of x and y is equal to the covariance divided by the standard deviation of x and the standard deviation of y. So again, something important. Oh, away. And the way that we can find the standard deviation then for this is we take the square root of the variance. And we can calculate what the variance was because, as I said, the covariance is x comma x. So I suppose we could also rewrite using these, like down here, that the correlation can be rewritten as the covariance of x comma y over square root of the covariance of x comma x times the square root of the covariance y comma y. Now the covariance, or sorry, the correlation is usually a measure, is a measure that's between -1 and 1. And so this is where it would be almost like that there's none. In here would be a weak. And as you go towards 1, that becomes a stronger correlation. And again, it's weak in kind of this area. And as we go to the extreme, the -1, this is becoming a stronger. So just some basic remarks about this is that if the correlation is equal to 0, then x and y are said to be uncorrelated. And the other thing is that when we have the correlation is equal to 0, it does not imply that x and y are independent. Now we'll have to talk about what independence is in a couple of seconds, but again, it's not stating that x and y, if I know what x is, that I really don't have any further information about y. This is what it's saying is that's not the case. It's simply stating that there is an absence of a linear relationship between x and y. So it means that just because you could have something where the correlation is equal to 0, and that it just says that there's no linear relationship, there could be a relationship like that is nonlinear. So is there any questions so far about this? Okay. So a question that comes up a lot is, what is the difference then between the covariance and the correlation? And the covariance, again, is a measure of direction between the two variables. With the covariance, if it's positive, the points are going from the bottom left to the top right if you're looking at the xy axis. And if it's negative, it's going downward from the top right, or sorry, the top left to the bottom right on the xy. And if it's near 0, then the points have no general direction. Now, both covariance and correlation are positive when the variables tend in the same direction, and they're negative when the variables tend in the opposite directions. However, the correlation coefficient is always between -1 and 1, and it indicates a strong relationship when it gets to either the -1 or the 1. Whereas the covariance, it can be any value. Okay. Number 6. Now, in this case, when we did in chapter 2, we introduced the idea of independence of two events. And we said that for two events, A and B, if the probability, and I'm using A and B, so I should use A and B. So let's say the event A given B, so that's the probability of A, given that B has occurred, is equal to the probability of A and B occurring divided by B occurring. Because again, we were told that B has occurred. And so that's the conditional probability. Now, if we rearrange that to the probability of A and B is equal to A given B times B. Now, what independence means is that if I knew information about A, it would give me information about B and vice versa. So in this case, it wouldn't give me any information. So again, when I have this conditional probability and I'm given information about B, this is something that I want to kind of neglect. So what we'll do is we can say that it's the probability of A times the probability of B is equal to the intersection. And this is what the definition is that we used. That if A and B are two events, if the probabilities of A and B is equal to the probability the probability of A times the probability of B, then we say that it's independent. And if the condition is not met, then A and B are said to be dependent events. And we have an analogous definition for the independence of two random variables. So what we say is that for two random variables x and y, if for every pair of x and y, in the discrete case, we say that the joint probability mass function is equal to the individual marginal distributions. So we have the marginal distribution for x times the marginal distribution for y. Okay. And also, if x and y are continuous, then instead of using the probability mass function, the joint probability mass function, we'll use the joint probability density function. So again, the probability density function, x and y, is equal to the individual marginal PDFs. So we have the marginal probability of x times the marginal probability of y. And so if it's true for every x and y, then they are said to be independent. Now, if the condition is not met, then x and y are said to be dependent random variables. So what we're saying is that two variables are independent if their joint PMF or the joint PDF is the product of the two marginal PMFs or the marginal PDFs. And so intuitively, again, it's going back to what we thought of initially with independence when we were talking about the two events, that if you know the value of one of the random variables, say like you know what the random variable value is, this one, this will not help you or provide any sort of information about what the value of the other one should be. And that's what we mean by independent. Knowing that something about this doesn't give you any information about the other one. Okay. So something about conditional probabilities, independent random variables. Let's look at this. We have a theorem. Make sure I label my pages. Here we go, page 7. Suppose that x and y are independent and joint continuous random variables, then the expected value of xy is equal to e of x times e of y. Okay, again, be very careful. Again, if this only is true, you can only multiply these expected values if they are independent. So here's the proof. Since x and y are independent, it means I can use the joint probability density function is equal to the marginal probability density function of x times the marginal probability density function of y. So that's the marginal PDF of x. Over here is the marginal PDF of y. So what does this mean? Well, let's start off then with the definition of what x and y should be. So knowing from what we had originally, from what we did at the beginning of the class, from our warm-up exercise, it should be the integral, the double integral of xy times the probability. So that's what we'll do. Using that, we have x times y times the joint probability density function so now we're done with that. The next thing we can do is, since x and y are independent, we'll replace that. So we'll have from minus infinity to infinity. Again, x and y is still there. But instead of the f of x, we'll use the condition about it being independent. Okay. Then the next thing that we can do is, since these are independent, I can actually break up these integrals into two separate integrals. So I'll have the integral of x times the marginal of x times the integral y times fy of dy, and right there is our definition of mu of x. Right here is our definition of mu of y. And so we've proved it. So there it is. That if you have two random variables, x and y, that are independent and they're continuous, then the expected value of xy is equal to the expected value of x times the expected value of y. So here's the conditional distribution. So in chapter 2, we define the conditional probability of an event E given F has occurred as so thinking back, what we had again was the probability of E and F happening divided by the probability that happened. And again, this is provided that f is positive. The probability of f is positive. Again, because we don't want to have a denominator that goes to 0. And so what we can actually do is apply the same idea to joint random variables. So in the discrete case, what I have is, let's say x and y are two discrete random variables, and you have a joint probability mass function, and you have a marginal probability mass function. Then for any value of x, for which, again, the marginal probability mass function is greater than 0, then the conditional PMF of y given x is equal to this. The probability function is y given x is equal to the probability function, the joint probability function, divided by the marginal of x. So again, this is what is important, be very careful. So again, this is the given. So again, this is given. And that's what that's what goes into the denominator. So you can, again, it's the joint PDF, or PMF in this case, dividing it by the marginal PMF. Okay. So in the continuous case, again, we let x and y be a continuous random variable with a joint PDF, so it's a probability density now, and a marginal probability density function f of x. Then for any value of x for which it's positive, the conditional PDF of y given x is, so instead of writing p's in this case, I'll use f's. And again, I have the joint density function divided by the marginal. And in this case, we're given x. So the marginal distribution for x for y over the entire real line. So what we should do then is do a couple of examples. Now that we have all the terminology set, again, I should probably put this in, box this up. Same thing over here. Oops, there we go. So here is our example. Okay, so after normal working hours, so like when the bank closes, the TD Bank near my house operates a drive-through window and an ATM inside. So on a randomly selected day, we'll let X be the proportion of time that the drive-through window is in use, or at least that there's one customer being served or waiting to be served. And we'll let y be the proportion of time that the inside ATM is in use. So I should write down what the joint probability density function of x and y should be. So let me write this down. I'll use this color. So we'll say 6/5 times x plus y squared. And we're going to say that this is between 0 and 1 for x and 0 for 1 for y. And we're going to say 0 otherwise. So outside of that, it's 0. So the first question we're asked is, what is the conditional probability density function? So again, that's the conditional PDF of y, given that x is equal to 0.8. So converting that into words, what it's asking is what's the conditional probability density function? So it's for y, given that x is equal to 0.8. And so using our definition, which is this, we substitute our values in. So f of y, so in this case it's going to be x comma y, so it's going to be 0.8 comma y divided by the marginal PDF of x, but it's going to be evaluated at 0.8. Okay. Now before I can go, I can put this in, I can put this part in here. I can put the 6/5 times 0.8 plus y squared. So that's fine. But I don't have my marginal density function yet. So what I should do is find it. And let's use a different color. So what I need to do is I need to find what that is. So the way that I would do that is I have to integrate this joint probability density function for y. And when I do that, I'll have 6/5 x plus y squared dy. And the more, like, this is the important part, is being able to set up this integral too. So again, I have to integrate from 0 to 1. And if you do this, then what you get is 6/5 x plus 2/5. So again, you should be able to integrate that yourself. So putting this back into here, I'll substitute in the x, the 0.8, so it's 6/5 times 0.8 plus the 2/5. And then what we're left with is 1/34 times 24 plus 30y squared. So that's the conditional PDF of y given that x is equal to 0.8. So the next part is what is the probability that the inside ATM is busy at most half the time, given that 80% of the time that the drive-through window is in use? So again, we have to read this and convert this to mathematical notation. And so it's asking for the probability. So it's the probability that the inside ATM, so that's, in this case, it's going to be y. So y is at most half, so let's say 0.5 again. Given that 80% of the time that the drive-through window is in use, so that x is equal to 0.8. So now what we do is we'll we need our conditional function, so that's what we need, is our y given x. So this is y given that x is equal to 0.8. And so we're going to integrate this in the y direction, so we have dy. And for those of you that are in the chat, what should I put for my integration, my limits of integration? Given that y has to be less than or equal to 0.5. Yep. That's good. From 0 to 0.5. Yep. Excellent. Now, what we can do next is, so we're going to integrate from 0 to 0.5, and we need this function, but good thing that we did this in part A. So this is what we need. And so I'll substitute that in here, down here. So down here, I need to have as 1/34 times 24 plus 30y squared dy. And you can use whatever methods you want to do. But, you know, you may find that some calculators may be even able to give you an integral. So for instance, here's a Casio calculator. And let's do the integral. I'll punch in my 1/34 times 24 plus 30. And in this case, I'm going to use x here. Again, for the calculator. Square that. And I want to go from 0 to 0.5. And the calculator will chug along. And what I get is let's go 0.390. Now, again, what we could do is we should do this instead of using the calculator. I will do it by hand. Make sure that I didn't. Maybe the calculator's wrong. Maybe I punched it in incorrectly, but we should be able to do this ourselves. So I can bring out the. So again, 1/34. We'll have this times the 24 dy, plus we'll have the integral of the 30/34 y squared dy. So again, you'll have 24/34 integrating dy from 0 to 5. So what you would get then is a y, and so that would be 0.5 minus 0, so that should be 0.5 plus 30/34, and you'll have 1/3 y cubed from 0 to 1, and so what you should get is so when we substitute in here, we'll get the 1 cubed, and so it's just 1/3 minus 0. So we can simplify that so that we're left with 12. over here is 10. So what I'm really left with is 12 over 34 plus 10 over 34. I should have. So yeah, that would have been 22 over 34 or 11 over 17. And 11 over 17 should give us, uh-oh. Oh, good, yes, I made a mistake. Thank you. Yes, thank you for catching that. So I should get 12 over 34. Well, I should add up this here. So 1/3 times 0.5 cubed times the 30 over 34. And add the 12 over 34, which gets me what I needed. The 0.3897. Same idea, right there. Okay. So is everyone satisfied with the integration then? With this number then? Yes, and so again, yeah, it should have been from 0 to 0.5 for all of those integrals. Okay. So the next part is part C. What is the expected proportion of time that the inside ATM is busy, given that 80% of the time that the drive-through window is in use? So again, this is what they call a conditional expectation. Because again, it's saying what's the expected proportion of time. So if you want to think about it, they're asking us about the proportion of time of the ATM, so it's the conditional of y given x. So it's y given that x equals 0.8. That's what we want. But it's the expected value. So then we know what the expected value looks like. Usually the expected is the integral of x times the probability density function dx. So in this case, I'm going to do the same thing. So that's our function, that's our density function, and we're going to multiply it by x, and then we're going to integrate it by, so in this case, I've already set what the x is going to be. That's going to be the 0.8, and so I don't want to integrate again with the x. I want to integrate for y. So it's not the x here. We'll use y. And so we get dy here. Okay. And for this, we'll go from -infinity to infinity. And, okay, I guess that was another bot. Okay. Thank you, Eric, for that. So this is the expected value of y given that x is equal to 0.8. So that is the conditional expectation that we're going to calculate. So we'll do the minus infinity to infinity of, we'll use our function here. Well, actually, this is the conditional density function that we want, because again, that's what we have down here. So again, same function that we'll plop in here. So it's 1/34 times 24 plus 30y squared. We'll have dy so I can bring out the 1/34 in front. We're going to go from minus infinity to infinity of 24y plus 30y cubed dy And is there any further, well, does anyone see an issue yet? Or maybe a simplification I could do. I could go from 0 to infinity. Someone's mentioning also the area that I'm integrating over. Yeah, what am I think I can even go even smaller than from 0 to infinity. Yes, I can go from 0 to 1. Okay. And I'm running out of room, so I'll just grab another sheet of paper. I'll just copy this down here. So I have 1/34 integrating from 0 to 1, 24y plus 30y to the 4th dy so it goes up plus 30 fifth oh I have to be careful. I don't know why. There we go. There we go. Just make sure I don't. There we go. So 3, this goes up to 4. from 0 to 1. So I have 1/34 times 12 plus 30 over 4. So that gives me, 39 over 68. Which is equal to 0.5735. Make sure that. Okay. So again, that is our conditional expectation. So what that is saying, that roughly 57% of the time the inside ATM is busy, given that 80% of the time the drive-through is busy. Yep. And similarly, like you could use a calculator, I suppose, on this kind of, but again, it's a polynomial, so we should be able to integrate that fairly easy without having to use a calculator. But again, we can always check our work times, we'll have 24x plus 30x cubed. We're going to go from 0 to 1. And yep, we can match the same. So that's good to know. It's a good way to check. All right. So let's work on our next example. I think that was page 8, and here's page. Okay, yes, we can take a break. That would be a good time to take our pause. And then we'll take a 10-minute break and we'll return to work on this last example here. Okay, so let's resume back to our lecture. So we're going to start off with this example. Okay, and hopefully everyone can hear me okay. The audio is okay? Okay, perfect. So let's start up with this example. So suppose a large number of customers in the Kingston area have purchased a homeowner's policy and an automobile policy from an insurance agency. And we're going to, for each type of policy, there's a deductible that must be specified. Now, a deductible is the amount that one pays out of pocket before an insurance agency will pay any expenses. So what that means is if there's some sort of damage, this is the amount that you have to pay before the insurance company. So, like for example, the automobile policy, the deductible amounts are available is $100 and $250. And for a homeowner's policy, the deductible amounts available, and it's not area, it's R. Oops. R, $0, $100, and $200. So an individual with both types of policy is randomly selected from the insurance agency's files. They're going to say let X denote the deductible amount for the auto policy, and Y is the amount or the deductible amount on the homeowner's policy. And so we have a joint probability table, and it's given below right here. So the first thing we're asked to do is calculate the probability that, so Y, meaning that the deductible amount on the homeowner's policy is greater than or equal to 100. So here we go. It's the probability that Y is greater than 100. And really, what I just need to do is look for where it's 100. So this is for Y here. I just need to go from 0, 100, 200. And so anything that's greater than or equal to 100. So it's just these entries right here. So all I have to do is add them up. So 0.1 plus 0.2 plus 0.15 plus 0.3. That gives me 0.75. Now the next thing I need to do is we'll do the marginal probability mass function. So what that means is I should have to do the margin. So I add up for this the 0.2, the 0.1, and the 0.2. So that's 0.5. And same thing for this row here, 0.5 plus 0.15 plus 0.3. That gives me, so 0.3 plus 0.2 gives me 0.5. So it's 0.5. So the marginal, so this is a discrete variable. So I have 0.5 if X is equal to 100 and 250, Otherwise, it'll be 0. Okay. Switch pens. Let's use this color. Then we do the margin for y. So again, I go down these columns now for y. So I have the marginal for y. Now in this case, this is a quarter. This is a quarter. And this is 0.5. So I get 0.25 if it's 0 or 100. It's 0.5. Oops, and I wrote x. Sorry, I meant to say y. Is equal to 200 and 0 otherwise. And so that's the marginal PMF of y. And so the question is now, are the random variables x and y independent random variables? So what we should do is go back to our notes for what independent random variable means. And what it says is that, again, we're working in the discrete case, that I should be able to multiply the marginal for x times the marginal of y for that point x, y. And that should be the same. If it's not, and again, for every point, so if I find one case where it fails, then it's not independent. It means that it is dependent then. Okay? So if I go back to my sheets here, I have to use my marginal PMF for x and y. So again, for it to be independent, that the probability of x times y, sorry, the joint probability of x and y is equal to the marginal of x times the marginal of y for every pair xy. Okay, so what I'll do is, let's pick 100 here. So we'll pick the point 100, 100. So I will then calculate the marginals here. So if I want 100 for this marginal, I put this value in here and x equals 100, so that will spit out 0.5 times, and then if I do 100 in the marginal of y, that will, if I put in 100, what spits out is 0.25. Now 0.5 times 0.25 gives me 0.125. Now let's check what the probability of 100 is. And if I look it up in the table, 100 and 100 is 0.1. So that's 0.1 right here. And this is not equal to each other then. So X and Y are not independent. And again, the independence requires that every entry, every entry in the joint probability table be the product of the corresponding rows and column marginal probabilities. Okay. So the next question that we have, well, we're still working with this long example. So we've calculated the probability that the deductible on a homeowner's policy is greater than 100. We've calculated the marginals of the Y and X. We showed that X and Y are not independent random variables. Well, the next thing that we can do is we'll calculate what the expected value of X is. And the expected value is equal to the sum of all the X's. So it's X times the marginal function. So it'll be 100 times 0.5 plus 250 times 0.5 and that should give me 175. Next question is, what is the expected value of Y? So now instead of using the marginal of X, I'll be using Y instead. And again, I should swap out the X for Y. So I use the same thing again. I'll have 0 times 0.25 plus 100 times 0.25 plus 200 times 0.5 and 0 otherwise. And if I put that in, so that I don't have to worry about, I get 125. Okay. Now, what I'm going to do is we're going to calculate the covariance of X and Y. Now, I think we've done a similar problem like this before, and we probably used something like the summation of X minus mu of X times Y minus mu of Y times the probability. And so that this is probably a double sum. We could do that, or let's use what we've learned today, which was that the expected value of xy minus mu x mu y will give us the covariance of xy. So to calculate xy, what I need is the sum of xy times its probability. Okay, and so you can do the same thing, just working through the rows. I wish I had some more. Let's see, how can I fit this all on the same page? Oops. Okay. So I'll just write that up here. Hopefully I can. So that's where we have to do. We have to do something like that. So it's going to be xy times its probability. So what I need to do is 100. So it'll be 100 times 0 times its probability. So I'm doing, this is my coordinate. So it's 100 times 100 comma 0. And then this is the probability. So again, 0.2 plus 100 times 100 times 0.1 plus 100 times 200 times its probability. And doing the second row, 250 times 0 times 0.05 and almost done. Okay, and if you punch this into a calculator, what I got is 23,750. Okay, so I get 23,750. Then I'm going to subtract that from, I need to use my mu x, which was 175. Times the expected value of y, so that's 125. And if we plug this into a calculator, we get 1,875. So at the bottom here, I said give an interpretation. And so what this says is that the covariance is positive. Okay. So if you're thinking of it as an XY plane, it's doing something like this. It's going in a diagonal upwards, which means then that that if you have something up here like quite high, that means that you have a large deductible for both. So you would have a large deductible for the homeowner and the auto insurance. So large deductibles for the auto policy. Tend to occur with large deductibles for homeowners policy. And similarly, small deductibles. So again, kind of in this area down here. For auto policy, tend to occur with small deductibles for the homeowners policy. Okay. The next thing that we have is we want to calculate the probability that the homeowner's policy is greater than or equal to 100 given that X equals 100. So So, does anyone have any guesses on what we should do? Yep, the joint PMF over the marginal PMF of X. Yep. Yeah, so basically what we want is we want it where y is greater than or equal to 100 and x is equal to 100 divided by the probability that x is equal to 100. So I can calculate that. So that's the probability of the marginal down here. Yes. So we're going to use this, And the other thing that we need to do is I need to have the PMF. So I need, here is where it's going to be 100. And in the next part right here, I'm going to say that y has to be greater than or equal to 100. Okay, so we can start to fill this in. So for here, we just looked that up. So it's the marginal for 100. So right here, it's just 0.5. So we'll put that here, 0.5. And the next thing that we need to do is go and look at all the ones where it's x is 100 and y is 100 and greater. So I just need this one where it's 100, 100 plus 100, 200. So I get 0.1 plus 0.2 over 0.5. So I get 0.3 over 0.5, 3/5. Or you can think of that in decimal is 60%, or 0.6. Now, the other way that you can think of that is, given that x is equal to 100, so again, you start to think about just looking at this one row here. So you're just looking at this one row, and then, so that forms your denominator. This is kind of the space now. You're just restricting yourself to what you see here in the pink. So that's 0.5, right? And then you want it to be x equals 100, so it's this, and then the ones, so that's all the possibilities that you have, and you want that y is greater than 100. So then out of that pink here, what you'll want is the values where it's 100 or more. So that's 0.1 plus 0.2. So that gives you the 0.3. So you can think of it as this. You got, this is the ones that you want is up here. And down here is your highlighted. So again, the 0.1 plus 0.2 all over 0.5. Then we have to calculate the probability that x equals 100 given that y is greater than or equal to 100. So, same thing. I can write the probability of x equals 100 and y is greater than 100. Again, I'm just using my conditional probability. And in the denominator now, it's the probability that y is greater than or equal to 100. So now we're working in this kind of space in here because this is where y is greater than or equal to 100. So I just write down 0.1 plus 0.2 plus 0.15 plus 0.3. So I get my probability that y is greater than or equal to 100. Or I could just look at what I had done for part A. So Okay, and we know that this will be 0.75. And then the next part is I need to do where x is equal to 100 and y is greater than or equal to 100. So that just restricts me to, again, this row right here. So I'm just going to restrict myself right here. So I have 0.1 plus 0.2. So that gives me 0.3. And so I have 0.3 divided by 0.75. This gives me 0.4. So again, we should give some sort of interpretation. What that means is that, 60% of, now the y in this case is the homeowner's policy. So 60% of homeowner policy holders have 100 or more deductible given that the holder has a $100 deductible on, in this case, X is the on auto policy. And lastly, again, this says that 40% of $100 deductible auto, in this case, X is, an auto policy. So 40% of $100 holders given that the homeowner's policy has a $100 or more deductible. And that's the end of our lecture. So what we were able to do is, again, if you have two random variables and they have a covariance, they somehow influence one another, they're not independent, you can actually come up with some interesting conclusions. So again, given that you have some information in this case that an auto policy has a $100 deductible, what's the probability that that holder has the homeowner's policy that has a $100 or more deductible? And so it's a 60% chance that they do have a policy that's $100 or more deductible. So what sections are we covering next in Devore? So the next section that we plan to cover is we plan to look at going into section 6.1 and 6.2. So maybe I'll put that right here. So the next sections, 6.1 and 6.2. Okay. Thank you everyone for tuning in. And again, if you have any questions, send me an email. We can always set up appointments. Okay. Everyone else, check your grades. They're posted on Moodle. And without that, thank you. Oh, is this it for probability and the rest is stats? Yeah, I think so. It'll probably be, the remainder should be like statistics. Yeah. Okay. Take care, everyone. Goodbye.